Hi guys, and welcome to our third tutorial under the topic work, energy and power. There's a small mistake here. I know here it says tutorial 1. That's supposed to be tutorial number 3 because tutorial number 1 has already been done. Okay, let's get into it. So we're solving problems again today. Question 1. The driver of a 1.00 times 10 to the power 3 kg car traveling on the interstate at 35.0 meters per second slams on his brakes to avoid hitting a second vehicle in front of him, which had come to rest because of congestion ahead. After the brakes are applied, a constant kinetic friction force of magnitude 8.00 times 10 to the power 3 newtons acts on the car. Ignore air resistance. Part A of question 1. At what minimum distance should the brakes be applied to avoid a collision with the other vehicle? Okay. Part B. If the distance between the vehicles is initially only 30.0 meters, at what speed would the collision occur? All right. So first things first, let's just simply put down our data here. So I've been given the mass of the car as 1.00 times 10 to the power 3 kgs. The kinetic friction force, which is bringing this to rest, is 8.00 times 10 to the power 3 newtons, which is 8,000. And then the initial velocity VI is given by 35 meters per second. And then the final velocity, of course, is going to be 0.0 meters per square seconds because it has to stop before it hits the other vehicle, right? So to solve this problem here, we're going to use the work energy theorem. Remember, according to the work energy theorem, the external work done on a system is equivalent to the change in the kinetic energy of that particular system, provided there's no change in the gravitational potential energy. And so that's what we have written down here to solve part A. And actually part B will also be solved using this, so that equation works for both parts. Okay. So now, since work is the product of force and distance, which happen to be the same direction, we can replace that net work done there by the product of force and distance. And of course, we also have to include the trigonometric part because that's the part which brings our force or our displacement in the same direction as the force. So when we come here, notice what we have here. We have Ft, which happens to be the force, the kinetic friction force acting on this. Cos theta, we multiply that by d, we'll be able to get a value of our work on this side, and then we can get the change in kinetic energy on the other side. So from here, it's just a matter of substitution. The force was given before as 8.0 times 10 to the power 3, and so that's what you'll see in the next step. Let me just highlight the whole thing here so we can see it all. So what we're doing here is we've substituted a value for that F. Cos theta. Now, remember, the question is saying this force which we have been given here is the average kinetic friction force. So that means this force is actually opposing the motion. Okay? So if our vehicle is moving in this direction, then that force acts in the opposite direction. If that force is opposing, the displacement is in the direction of motion, isn't it? So when you look at the angle between these two, notice that's 180 degrees. And that's why you see we have 180 degrees here. So we multiply that by distance d, which we don't know, which we are trying to find actually. That part of the equation is done. So we multiply 8.00 times 10 to the power 3 cos 180. We get ourselves a negative 8,000 multiplied by d. And then we come to this other side. So the final kinetic energy is going to be 0 because we're looking for the minimum distance at which it is going to stop. So when it stops, the final velocity is going to be 0, isn't it? But of course, we know the initial velocity is 35 meters per second. So that's what we've substituted there. And then when you come to the next step here, notice what you have. So we have negative 8,000 D on this side, and then we have 0 minus, what is this? This is 612,500. Okay, and then to get the value of D there, we simply just divide both sides of this by negative 8,000. So we divide negative 8,000 into 612,500. We get ourselves a value equals to 76.56 meters. And that happens to be the solution for part 1A. For B, it's going to be similar, but now what we have been told is this. For part B, we are saying the vehicle is initially only 30 meters away from the car which is in front of it. That means it's going to hit into the car because it needs that 76.56 meters for it to completely stop before hitting that when it's traveling at that initial speed and it's being slowed down by a force equals to 8,000 newtons. So now we are looking for the speed at which the first car is going to hit the second car with. So again, all we need to do here is to apply the work energy theorem. So we're going to do almost exactly the same thing, but of course this time we know the distance on this side, right? We know the distance here has been given as 30, or this side here has been given as 30. So we'll do the same thing. So we say 8.00 times 10 to the power 3 cos 180, because the distance, or rather the vector displacement and the frictional force, kinetic friction force, are still in the opposite directions. All right, so let's just highlight the whole thing. Let's start from here all the way until there. Okay, so what we have done here is we have replaced this by 8,000, which is 8.00 times 10 to the power 3. Cos 180, because they are in opposite directions, and then we'll put our distance 30 here because that's what we're given in the question. And then this side, of course, we have to get the difference in the, or rather the change in the kinetic energy. So this here is the final kinetic energy, half mvf squared, where vf is the final velocity. And remember, the question says with what velocity is it going to strike the second car. So we're actually looking for final velocity, which is this part here, so we can maintain that. And then the initial kinetic energy will not change. That's half multiplied by the mass multiplied by the square of the initial velocity. So when we work this out, we are going to have on this side here, oh sorry about that, on this side here, when we multiply throughout there, we get negative 240,000, and then here when we multiply 1 point here, when we multiply 1.00 times 10 to the power 3 by half, we get a 500. And then this side, that side is just the same as this part here, so we still get a negative 612,500 there. All right, so what we end up with now is an equation which we have here, an expression which we have here. So we can collect like terms here. How are you going to do that? We just get this 612,000 and take it to the other side. Of course, when it crosses the equal sign, it's going to become positive. So now we have this 612,500 minus 240,000. So that gives us 372,500. To get the value of VF, of course, first of all, we get rid of the 500. We divided both sides. It goes on this side. And when the 500 goes into 372,500, we get a 745. But then to get the value of VF here, we have to get the square root of that value. So we square root both sides of the equation, and that gives us a value of VF equals to 27.29 meters per second. That's part B of question number 1 solved. Let's move on to question number 2. So question 2, it looks short. Let's see how we can solve such a question. A 1.00 times 10 to the power 3 kg elevator car carries a maximum load of 8.00 times 10 to the power 2 kgs. Okay, so this is the load and that's the weight of the elevator itself. Okay, a constant frictional force of 4.00 times 10 to the power 3 newtons retards its motion upward. Retards, so that means it's opposing, it's in the opposite direction as the distance it's going to cover, right? As in the figure below. Okay, so when you look here, actually that's been summarized here, so you can see mg is acting downwards and the friction force is also acting downwards, but then we have a force acting upwards, which is this one here. Okay, then the question is saying what minimum power in kilowatts? It actually says in kilowatts, okay, and in horsepower. Okay, so what minimum power in kilowatts and in horsepower must the motor deliver to lift the fully loaded elevator at a constant speed of 3.00 meters per second? Okay, so constant speed means net force acting equals to 0. And if net force acting is equals to 0, then total upward forces plus total downward forces must be equal to 0. So mg plus F must be equal to this force here, the tension force, right? Okay, before we get into the solving here, let's just put our data down here so we can clearly refer to it. So m is equals to 1.8 times 10 to the power 3 kgs. G is 9.8 meters per square seconds. F is equals to 4.00 times 10 to the power 3 newtons. And V is equals to 3.0 meters per second. Now, power is the rate of doing work, or the time rate at which work is done. So that's this here. But then we can replace the work by its formula, where we are saying work done is F cos theta multiplied by D. Now, when you look at this very clearly here, you notice, of course, this here is your force. But then distance divided by time there is equals to speed. So that particular equation there can be written as power being equal to force multiplied by speed. So I'm saying you can write that as power being equal to force and multiplied by the velocity v. Okay, so now what we need to do is we need to get the value of our force and then of course multiply that by the speed, right? So to get the value of our force, we're going to have to apply this equation here. The total sum of all forces in the y direction must be equal to 0. And so Ft plus mg plus, okay, let me put it like this. Ft is equal to mg plus F. On this side here, mg and F are going to be negative because they're in the opposite direction with this one here, Ft. So once we get that value of Ft, then we just have to multiply it by the speed, because remember, power is also given by the product of force and then the speed as well. All right, so let's move on to here now. So you can clearly see here now what we are doing is this part here. So, okay, first of all, let's finish with this one here. So Ft is equals to 1.8 times 10 to the power 3, which happens to be so what we are doing here is we're getting the total mass of the loaded elevator. Let me just go back here. So notice the elevator itself has a mass of 1.00 times 10 to the power 3. Then its maximum load is 8.00 times 10 to the power 2 kgs. And then the question here is saying we want the minimum power in kilowatts and in horsepower, which the motor must deliver to lift a fully loaded elevator. So for a fully loaded elevator, we have to add the masses, this one and this one, to come up with the mass, total mass of the elevator when it's fully loaded. And that's why you see the mass that we're going to use here is 1.8 times 10 to the power 3. That happens to be the sum of the maximum load and the mass of the elevator itself. So we multiply the maximum mass by 9.8, and then we add the friction force, which impedes the motion of this elevator. That gives us a 21,640 newtons. So we multiply that by the value of the speed, and then we get ourselves the value there of this is actually supposed to be negative, because the force of, okay, let's just go back here first of all. Let's see, what does it say? It says oh, no, it doesn't have to be negative. Why? Because the force we're looking at here is the force which is being delivered here by the motor. So this motor here is applying a force upwards, and then the distance also is upwards, and the speed is also upwards. So the angle between the direction of motion and the force is the same, is zero, because they're in the same direction. Okay, and so when we do that, we get ourselves a 64,920 watts. Now this value I've got here is in watts. Okay, so now we need to convert this into kilowatts. Remember, that's what the question says, isn't it? It says in kilowatts and in horsepowers. So to do that, you need relations between the two. So 1 kilowatt is equivalent to 1,000 watts. So to get that, simply just divide this value here by 1,000. That will give you an amount of power in kilowatts. So we divide that by 1,000, we should be getting 64.92 kilowatts. 64.92 kilowatts for the first part. Then for the second part, of course, the relation between a watt and a horsepower is that 1 watt is equivalent to how many horsepowers? That's about okay, now this value of power which we have obtained here is in watts, but remember the question says we need to find this amount of power in kilowatts and also in horsepower. So 1 kilowatt, we need to use a relation to do that. 1 kilowatt is equivalent to 1,000 watts. So to get this value in kilowatts, all we need to do is divide this value here by 1,000. And then what we should be getting when we do that is 64.92 kilowatts. And then for horsepowers also, we need to remember the relation between a horsepower and a watt. So 1 horsepower, which we usually abbreviate as HP, is equals to 746 watts. Okay, and so to do this, you simply just have to divide this value here by 746. Whatever value you have, it will give you an amount of power in horsepower, sorry. Okay, and so that's how you deal with the horsepower. But once you found the power here in watts, it shouldn't be difficult for you to change it into kilowatts and also to change it into horsepower, provided you remember this relation for horsepower and you remember that 1 kilowatt is equivalent to 1,000 watts. Okay, done for now. I'll see you in the next tutorial.